Question 3. Let ABC be an acute angled triangle with AB being longer than AC. Let P be the intersection of the tangents to the circumcircle of ABC at B and C. The line through the midpoints of the line segments PB and PC meets lines AB and AC at X and Y respectively. Prove that the quadrilateral AXPY is cyclic. So let's study this configuration. We have triangle ABC, and we've marked in its angles using dots. So there's yellow and blue and red. We've drawn its circumcircle, and then we have drawn the tangent lines to the circumcircle at B and at C. Those two tangent lines meet at a point we call P. We're supposed to look at the line segment BP and the line segment CP and draw the line which passes through the midpoints of those two line segments. Here it is going across, and this horizontal line meets AB at X and AC at Y. Our ambition in life is to show that the points A, X, P and Y lie on a circle. There's some low-hanging fruit here. We can just fill in some angles using elementary circle geometry theorems. There's this famous theorem, angle in the alternate segment, which applies when you have a tangent to a circle. And that applies in various ways. We get these two red dotted angles, a pair of vertically opposite red dotted angles around B, and a similar pair of vertically opposite blue angles at C. And also there's this yellow angle here and here. And they're all obtained by applying angle in the alternate segment. So that's a good start. So to make further progress, we have to do some geometry, and that takes the form of, well, a construction line. So draw a line through P which is parallel to BC. There it is. And let this new line through P meet the line AB at D and the line AC at E. Now you look at this diagram, you see all sorts of similar triangles. The important thing is that the point X is the midpoint of BD, and the point Y is the midpoint of CE. Now, I've just said that casually. If you're writing up a BMO2 argument, you've got to supply the details. But I agree, it's pretty obvious from the picture, but you should spell that out carefully. So we have these three parallel lines, BC, XY, and DE, and we have transversals, the lines AB and AC, cutting across them. That means that you have all sorts of angle facts in play. In particular, this angle here is going to be blue, corresponding to the blue angle at B here, and the angle here is going to be red, corresponding to the red angle at C. Now look at triangles PBD and triangle PEC. Two of their angles match up. They come in equal pairs. And so the third angles match as well, and those are two similar triangles. They're not only similar to each other, because of what the angles are, they're both similar to triangle ACB. And I said that the wrong way round deliberately, because there's an indirect similarity between ACB and the triangles PBD and PEC. The similarity between PBD and PEC takes the midpoint of this side to the midpoint of this side. That is to say, the similarity carries x to y. That means that you get more angle equalities. I've drawn in magenta and green angles here, and the same angles occur over here, but transposed. In fact, you could get from this triangle to that triangle by rotating and shrinking. Anyway, you've got these extra angle equalities. And notice, by the way, that magenta plus green is actually the angle at A, so it was originally yellow. So yellow equals magenta plus green. And so now we're ready to finish. The plan is to show that AXPY is cyclic because it has a pair of opposite angles which add up to 180 degrees. So this angle up at A, originally marked with a yellow dot, we've established that's the same as green plus magenta. The opposite angle in the quadrilateral AXPY is here, and that's almost a straight line. We just have to remove this angle and this angle. So this angle, XPY, is 180 minus a magenta minus a green. But that's exactly what you want. The two opposite angles add up to 180. So there is a circle that passes through A, X, P, and Y. And we're done. There's some advanced Euclidean geometry going on hiding behind this question. So I thought you might like to have a peek behind the curtain. So let's look at a simplified version of the diagram. We have triangle ABC, as before, with a circumcircle. And we've drawn the tangents at B and at C to meet at P. We've produced the line BC, so it's now a long horizontal, and we've drawn the tangent line to the circumcircle at A. And that line cuts BC at a new point, Q. Now, there are two lines which are tangent to the circumcircle, drawn from Q. One is the line AQ, but there's another one down here. And it touches the circumcircle at a point R. Now look at the diagram. Can you spot something interesting about this configuration? Look for a collinearity. As I expect some of you observed, the points A, R, and P lie on a straight line. This is called the Simidian line, or the capital A Simidian line, because it's been constructed to go through the vertex A of triangle ABC. I'll explain where this rather unusual name Simidian comes from shortly. So now we have these collinear points, A, R, and P. You feel an overwhelming urge to enlarge from A with an appropriate scale factor to carry R to P. And what that will do is to enlarge the circle ABC to a new circle which passes through A and P. And actually that's the circle that we were studying in the solution, but we're not there yet. So what do we do next? So now what we do is to produce the line AB until it meets the new circle again at a point called X question mark. It's going to be X later. And then we produce the line AC until it meets the new circle again at a point Y question mark, which is going to be Y. The problem now reduces to showing that X equals X question mark and Y equals Y question mark. And we can do this by taking the line through X question mark and Y question mark and showing, after doing some maths, that this line meets BP and CP at their respective midpoints. And that would be another way of approaching the problem. So this new line we have just constructed, the A symmedian of this triangle, makes angles at A as shown. I've also drawn in here the midpoint, M, of BC, and the median line from A through M. Now, there are angles which surround the median line at A as well. And the interesting thing about the relationship between the median line and the symmedian line is that those angles are swapped. So in a sense, the symmedian line is symmetric with the median line. Another way of saying it is that the symmedian line is the reflection of the median line in the angle bisector through A. Now, we have three symmedian lines, one through A, one through B, one through C. They meet at a point. We need a name for it. Let's call it the symmedian point. There's a rich and interesting theory associated with this point. In some sense, it is a celebrity triangle center. So you're familiar with the circumcircle and its center, the circumcenter. You're familiar with the incenter, the center of the incircle. You probably know about the centroid, where the three medians of a triangle meet. Some of you may know about the orthocenter, where the three altitudes of a triangle meet. That's four celebrity triangle centers. The symmedian point is the fifth celebrity triangle center, the one which is not spoken about very much. But there is a great theory, and you can read about it in any sufficiently advanced book on Euclidean geometry. And the Geometry of the Triangle by Jerry Leverscher is such a book published by United Kingdom Mathematics Trust. Those of you who are intrigued by this, I hope you enjoy finding out more.